calculus lesson, rates of change in natural and social sciences. All right, guys, do me a favor. Could you start working on this one? Pause the video and see how far you can get with it. All right, guys, we're back. And this is what you should have gotten. Um, the key point, this is a common mistake, by the way. A lot of the students, when they see this point, they just give me the x coordinate. Please don't do that. When we say, uh, what's going on? Oh, it doesn't work. Okay. So yeah, so when we say all points, I'm looking for actually coordinate points, right? So you set the uh, derivative of the f, set it equal to 0. We find the value, and then we have to plug that back into the equation, which is like right here. And when you do, you should end up with a 0, 0, negative 1, 2, 1, negative 2. And when you take the second derivative, that's what you should get, right? And over here, same thing. You set that equal to, take the derivative, here it is. Cosine of x, think of that as cosine of theta, right? Cosine of theta represents the x coordinate of the unit circle. X coordinates at 0 in the unit circle, here and here. And that's pi over 2 plus every 180 degrees thereafter, or pi k, where k is an integer, right? And when you plug in the value into this over here, oops, sorry. When you do that, when you plug it in, that's going to be 2. When you plug it in here at 3 pi over 2, the value is going to be negative 2, right? So there it is, right? And we're saying that the, oops, I forgot to write down that the k is all integers, right? Integer value. And when you take the derivative of this again, that cosine becomes negative sine of x. So here it is. All right, guys? All right. So let's take a look at this. Okay. So a lot of this we already know. Okay. So I'm just gonna like I'm not gonna write from scratch, but you should copy this image down. Let us say that, oops, like because sometimes we use f of t, sometimes we use s of t, um, especially when we're talking about a particle in space, right? And position of the particle, we tend to use letter s. But that being said, if you have some sort of function over the interval t1 and t2, and that's f of t1, f of t2, and draw this picture, okay? Now, what do you think is the average velocity? What do you think is the instant velocity? What do you think is acceleration? The speed, if you took physics, you should know that already. But remember, we have to define what a speed is in the context of the velocity and acceleration, right? Because we're going to talk about the particles in motion, right? And what is speeding up, speeding down, what is displacement, and what is the total distance traveled. They're two distinct things. All right, guys? All right, here we go. So let me zoom that in for you guys. Average velocity is a secant slope over an interval. So in our case, the average velocity over t1, t2 is f of t2 minus f of t1 divided by t2 minus t1. That is change in y and change in x. Okay, this capital delta tells us that it's a big change, right? Okay, so this is not literally change in y, change in x, but generally speaking. All right, instantaneous velocity is equal to this, and this right here is the definition of dy dx. That d right here, guys, is a small delta because it's a small change, okay? Right? And the acceleration we know is a rate of change of velocity with respect to time. So what that means is that you take the derivative of the velocity, you mean d dt of ds dt gives you d double prime, or you could write that as s double prime of t, okay? So you take the derivative twice, okay? Speed, by the way, is, if you didn't know, absolute value of velocity. Velocity could either be positive or negative. So velocity has a sense of direction. Can be positive or negative is directional, right? Whereas speed does not have a direction. Whether you're going forwards or backwards, you're going 5 miles per hour. Whereas when you say 5 miles per hour is the velocity, it means you're going forwards. When you have negative 5 miles per hour, you're going backwards. The difference between the speed and the velocity is that speed is not directional. Okay. All right, guys. So I'm going to talk about speeding up and speeding down or slowing down. Uh, most people would say slow down, slowing down. Okay. Well, anyways, the way that I would actually prefer to think about this is very visually, right? Is that when you are graphing this thing, position versus time, and that is supposed to be a horizontal line right here, guys, right? As long as you're moving away from horizontal line, your slope is increasing, isn't it? Your slope is increasing either more positive or more negative. But remember this, guys, we're looking for absolute value, right? So as long as you're peeling away from the horizontal, you're speeding up. Now, there's a second way to think about this. A lot of textbooks tend to either go do this and this or this or this. For me, that's too much memorization. Okay. Now let's look at this. In this particular picture, my velocity is increasing, isn't it? Which means that my acceleration is positive and my slope is positive. They're both positive. In this one, it's becoming more negative, meaning my velocity is decreasing. So acceleration is negative, and the velocity, which is a slope, is negative. Oh, they're both the same sign. Okay, if they're both positive and both negative, the product of them would be positive, right? If the product of the acceleration and the velocity is positive, we say that the particle is speeding up. But I personally prefer to look at the image. If it's possible for you to graph the particle motion, I would do that. Okay. So in other words, in this case, is moving forward, you're stepping on a gas, and then here you're moving backwards, and you're stepping on a gas, meaning you're increasing the speed going backwards. Does that make sense, guys? All right. This one case, once again, is that I would interpret this more by looking at the, if it's possible, to graph the position of the particle. And what's happening over here is that the position is getting closer to the horizontal, right? So in this case, let's look at this case here, guys, right? It's very steep and then it's becoming less steep. Very negative, less negative. So it's increasing. Look at that. And then my slope is negative, which means my velocity is negative. So one is positive, one is negative. Let's consider this case. Very positive and less positive. Slope, that is, right? So slope is decreasing. So it's negative. But it's generally slope is positive in this case, generally speaking. So it's opposite side, right? In this case, you're moving forward, you're stepping on a brake. Here, you're moving backwards, you're stepping on a brake, right? Anyways, the product of those two is negative. So if you don't do it analytically, like algebraically, you would do it this way. But if you could confirm that visually, that's even better. That's how you check your work as you do your problem, right? You need to know this and this. All right, guys. The displacement is the net change in position. So basically, this S of T2 minus S of T1, change in S, if that's the height difference, right? So if this is T1 and this is T2, the position at T2 is over here, position at T1 is over here. That difference in height, that's the displacement. However, total distance traveled is different. So for example, if you move up, down, and up again, the total displacement is not a displacement, it's a distance traveled. So you went up this way, you from here to down this way, from here you went up again, right? So that's the distance you traveled. So you got to add all of them up, right? So once again, from here to here you went up, but from here you went down. But from here you went up again. So that's the distance you travel. Guys, think of it this way. If you go around the track once, exactly once, your displacement is 0. But that doesn't mean that you didn't do any work, right? You went around the track. So that's what you're measuring, the distance traveled. Whether you're going forwards or backwards, it doesn't matter. You actually went the distance. So basically what we do is when it's going down like this, you want to put absolute value around it like this as you add individual. So you want to add all the positives and then absolute value of the negatives when it's going backwards. That'd be total distance traveled. Okie dokie, guys. All right. So do me a huge favor. This is the equation function of the particle, right? The position of the particle as a function of time in seconds, right? The distance is measured in meters, and the time we have is greater than or equal to 0. And do me a huge favor, guys. Go ahead and try these, and I will explain each one carefully. You can pause the video. All right, guys. I'm going to assume that you took some time to do this. This probably would have taken anywhere from 5 to 10 minutes or so, right? If you're not sure, it's okay. I will walk you through the problem, okay? All right. So that particular problem is right here. First of all, to find the velocity, you just take derivative, and we did, right? And then the derivative of the 3 is 0, and twice the 3t squared is 6t squared. 21 negative 21 times d. The derivative of t squared, which is 2t, gives you that. And the derivative of the 60t is 60. Now, when it says particles at rest, means the velocity is equal to 0. We set it equal to 0. And the key word is when, isn't it? When it says when, you're looking for the values of t, right? And then you want to solve for t when the velocity is equal to 0. And then we set what we found here equal to 0. This now becomes basically algebra 1, right? You factor, set it equal to 0, the t is equal to 25. But don't just leave it there, guys. Give it a complete response, which is to say the particle is at rest when t is equal to 2 or 5. When it's moving forwards or backwards. It's moving forwards when the velocity is positive. It's moving backwards when the velocity is negative. Right. Now that we have this value, we could draw a number line to figure out when it's positive or negative. So you do like, what do you call that thing? Sign analysis. Me personally, I don't do it that way because, I mean, you do that to introduce ideas. But look at this, guys. When you multiply that out, it's not t squared minus blah, 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 blah. The t squared is quadratic. Quadratic looks like this, right? So it means that it crosses at 0. So it looks like this. Above the x-axis is positive. Below the x-axis is negative. Positive, negative, positive. And then what you need to do is that you might have messed up. So plug in a value, see what happens, right? Let's see if you plug in, let's say 8. 8, that's positive. 8 minus 5, that's positive. Times positive, yep, it's positive. There you go. Okay. So you could do that, check it out, just make sure that you didn't make any mistakes. So if it's positive, it's forwards. If it's negative, it's go backwards. And there you go. Guys, make sure that you exclude the endpoints. Remember, it has to be greater than equal to 0. So greater than 0. So when it's 0, you need to exclude the value. When it's equal to 0, it's at rest. Remember that. Okay. All right. Find the position when the velocity is 24. I set the velocity function equal to 24 and solve for it. Once again, this is we've been doing this for like the past 3 years now, right? So please do me a favor, guys. Give me a complete answer. Velocity is 24 meters per second when t is equal to 1 in 6. Okay. All right. Now, and total distance traveled. I basically saw that S of t is cubic, so it kind of looks like this, right? was positive cubic, so it had to look like this, right? Knowing when it's at rest, I know it was like this. And at rest over here, I know it sort of looks like this, right? The curvature. And then I set the y-intercept is 3. So I knew that it had to go up, come down, and up again. But I need to plug in the values, right? To figure out what the values are. As it turns out, it's a 3, 55, 28, 80. That's the position of the particle at times equal to 0, 2, 5, and 7, respectively. So remember this, guys. This is the beginning and the end, right there. Those are the endpoints. And these are the 2 points in which you change the direction. So we need to know the distance that you travel from here to here, which I did over here. And what distance did you travel from here to here, going down? I did not change positions, guys. If I get a negative, I just make it positive. That's all. And then from 5 to 7, right, I subtract those two values. And when I add them up, it is 131 meters. There you go. All right. So when is it speeding up or slowing down? As I mentioned before, guys, I prefer to think of it this way. But I did go ahead and found the acceleration. And then the t is equal to 7 over 2, right? To the right is all positive, to the left is all negative. V of t, I just did it, overlaid the two graphs. See the product over here, guys? So basically, it's 0 here and here. Okay, let me put that in a different color. It's 0 here, here, and here. 0 times anything is 0, right? Right. And the rest, we say negative times positive is negative. That portion is what? Negative and negative, right? Makes it positive. Positive, negative is negative, and so on and so forth. Okay. Just be really careful. But look at this picture, guys. From here to here, this is S of t, by the way. We're slowing down. See that? It's approaching the horizontal, right? And from here to here, it's moving away. And from here to here, it's approaching the 0. And here, we're speeding up again, right? So if you look at the picture, it's very consistent with this image, okay? I would just double check it with the picture if I were you, okay? All right. Anyways, this is your turn. So it's very similar. The function is a little bit different. The idea is the same. Please do this at home. And then what we'll do is in the morning, you will go over this with your classmates within your group. All right, guys? All right. Okay. Let's look at this. Example 2. This is the position graph. And we need to answer some questions, right? Do me a huge favor. Why don't you go ahead and try to answer these questions, guys? After having done the previous question, this should be fairly doable. Please pause the video. Okay, we're back. So here are the answers. When it's moving to the left, it's decreasing. The idea here is that the slope is negative. It's negative here. So from 2 to 5, right? Exclusive in an open interval. When it's moving to the right, it's increasing, or the slope is positive. It's here, guys. That's what we do. Standing still, it's flat. It's horizontal, right? The slope is equal to 0, which is here and here. So I wrote that down. And what's the particle's graph of the velocity? Basically, the velocity is a slope. I'm drawing a slope graph. So from here to here, what's my slope? That's a 0. Boom. From here to here, though, from 2 to 5, my slope is -2. There you go. From 5 to 7, my slope is half. There you go. And then from 7 to 9, my slope is 0. So there you go. Now, there's a question of where, what I did was I just made the left-hand side solid and the right-hand side open, right? I'm sorry, that was supposed to be open. There you go. That's open. It really doesn't matter. We could talk about why later, but one thing that you can't do is they're both closed or both open, because look at this, at these points they're continuous, so the value has to exist somewhere. So where you saw open and closed, it really doesn't matter, as long as that they're not both closed or both open. One of them has to be closed. Okie dokie. All right. So, and then the last one is what is moving the fastest. The word move implies speed, right? Speed, moving fastest. So this is actually wrong then, right? Moving implies speed, right? Not velocity, but speed. So it's maximum value of absolute value of this. So I kind of made a boo-boo here. So the velocity here is absolute value of that is actually, what is it again, guys? -2, isn't it? Absolute value of that makes it 2. Oopsie. 2. And that goes from 2 to 5. Okay. 2 to 5. There you go. All right, guys, we're almost done. Okay. So I'm going to do a quick intro in Econ application. Is suppose there's a cost function, total cost that company incurs in producing X units of certain commodity, right? So that'll be known as a cost function. The number of items produced increase from X to X1 to X2, then there's an additional cost, right? That change in C, that capital, that delta right there implies an interval over a period of time. And the average cost of change of the cost is change in C over change in X. So that's what that is. Or this is a average cost at starting at X1 over a certain time period. So does that look familiar, guys? Yeah, this looks like a secant. It looks like a secant slope, doesn't it? Exactly. Secant slope, average. That's what we've been doing the whole time, right? Now, when we take that change of X to 0, guys, what happens? The instantaneous rate of change of cost with respect to number of item produced is called marginal cost. Oh, the marginal cost is the derivative. Yeah, that was it, right? Marginal cost at that point is the derivative at that point. That's all it is. So do me a huge favor, guys. Try to do this. Marginal cost. What's marginal cost again? What did I just say? There you go. At that point, and then we're going to talk about this in class together as well. Sounds good? All right. We're supposed to do linearization as well. We're going to be doing that in class as a synchronous learning. All right, guys? All right, guys. I'll see you tomorrow, okay? Good night.